For centuries, our idea of life has been, well, pretty limited, hasn't it? It's been a reflection in a very specific mirror, our own.
Exactly. Carbon-based, needing water, breathing, eating. Basically, things like us.
Right. When we've looked up at the night sky, we've often imagined life as, well, us, or maybe variations on the theme. But what if that mirror is just one tiny facet of a much grander, much stranger reality?
What if the universe is just teeming with forms of adaptive life so alien, so fundamentally different that our current definitions just fall apart?
Yeah, what if the very concept of life needs a complete overhaul? Today on the deep dive, we're not just expanding our minds, we're kind of taking a hammer to that mirror. We're guided by a truly groundbreaking work called Foundations for Adaptive Life, exploring viable substrates and emergent conditions. It's by Randolph Lilien, published just this year, 2025.
And it's not just another research paper. This feels more like a conceptual earthquake, a universal blueprint for understanding life in the most expansive terms possible.
Absolutely. Our mission today is to dive deep into what Lillian calls the AL, or adaptive life, Groupset. Think of it as a universal framework designed to define and identify life, whether it's hiding in a microscopic tidal pool right here on Earth.
Or maybe thriving within the superheated plasma of a distant star.
Mm-hmm.
Or even potentially within the coherent dance of quantum particles way out in interstellar space.
It absolutely pushes us beyond our familiar carbon-based assumptions. It dares us to consider what thriving truly means across the immense diversity of the cosmos. Now, a key insight that jumps out right from the start of this work, and it's one we really want you to carry with you through this discussion, is this. The AL Groupset offers a universal, substrate-independent definition of adaptive life.
And that's more than just a new idea. It's a really crucial shift in perspective. It gives us entirely new lenses for astrobiology, for theoretical biology.
Right. This framework isn't looking for specific molecules like DNA or RNA. It's looking for the fundamental principles of life, the underlying processes, the dynamic capabilities that allow a system to persist and prosper regardless of what it's made of or where it's found.
And what's truly compelling, I think, is how Lilien frames this whole concept. He says it's viewed through the lens of hypersymmetric coherence and resonance.
That sounds deep, almost poetic.
It is, but it's also deeply foundational. It suggests there's an underlying elegance, maybe an order, to the universe itself, like a kind of deep, interconnected harmony that fundamentally binds all the conditions necessary for life to emerge.
So not just random chance.
Maybe not entirely. It implies that life isn't just some chaotic accident, but maybe it emerges from intrinsic, almost beautiful symmetries within the universe itself, a universe perhaps inherently structured in some way to facilitate complexity.
Okay.
It hints that there are universal patterns, symmetries, these resonant frequencies maybe, that are at play, facilitating the very unfolding of complex adaptive systems, whatever they're made of.
All right, so we're going to deconstruct these powerful ideas piece by fascinating piece. Then we'll see how they all fit together to form this truly comprehensive picture of what adaptive life could be. We'll be applying this detailed deconstruction across all the possibilities Lillian lays out.
Okay, let's unpack this universal framework for adaptive life. Before we get into the 7 specific ingredients Lillian identifies, let's really try to nail down the core definition this document proposes.
Yeah.
Why is it such a profound game changer for how we think about life out there? It really challenges our human-centric biases, doesn't it?
Oh, absolutely. It completely does. What's revolutionary here is how the AL Groupset immediately moves beyond our very Earth-centric view. It defines adaptive life broadly as systems capable of thriving in varied settings by leveraging fundamental principles such as far from equilibrium stability, negentropy, coherence, and the capacity for evolution and self-organization.
Okay, so notice what's not in that definition. Exactly. There's no mention of specific components like DNA or cells or even carbon. It's all about the dynamic capabilities, the system's inherent ability to persist, to maintain itself, and to prosper amidst constant change.
Adaptability and resilience.
Right. The emphasis is squarely on adaptability and resilience across diverse environments. It suggests that life isn't a fixed state, something that just is. It's more of a dynamic process, a continuous state of becoming, of adjusting, self-regulating.
Like a verb, not just a noun.
Precisely. It's about how a system, whatever its composition, manages to maintain its organization and even flourish amidst the constant flux of its surroundings. And this is a truly profound shift in perspective because it broadens our search. We stop looking just for Earth-like conditions and start looking for any conditions that support these fundamental dynamic processes.
That immediately reshapes our entire search for extraterrestrial life, doesn't it? If we're not limiting ourselves to looking for little green men or even just carbon copies of ourselves.
Then we're not just stuck looking in the so-called Goldilocks zones anymore.
Right. It forces us to ask entirely new questions about what thriving truly means. It lets us consider life in places we once just dismissed as impossible. Extreme temperatures, weird pressures, bizarre energy sources.
Suddenly, they're potentially back on the table.
And right in the introduction, Lilien frames this through the lens of hypersymmetric coherence and resonance. It sounds, like I said, almost philosophical. For our listeners who are maybe more technically minded, what might such a hypersymmetry actually look like? Or what does it imply in, say, a plasma-based life form versus a crystalline one? Are we talking specific vibrational modes, energy state alignments, or something even more abstract?
That's a key insight, and it's where the framework really elevates our thinking beyond just listing conditions. If we connect this to the bigger picture, hypersymmetric coherence and resonance suggests a deeper, unifying principle woven into the very fabric of the universe. Think of hypersymmetry not just as, visual symmetry like a snowflake, but as a deeper, maybe hidden order in the fundamental laws of physics and information. It might dictate specific energetic or informational pathways that are inherently stable or efficient or just conducive to the emergence of complexity.
So for a plasma-based life form.
Well, for that, this hypersymmetry could manifest as, say, the optimal alignment of electromagnetic fields, maybe creating stable, self-organizing vortices or structures within the plasma that leverage its inherent energetic properties in a way that's maximally efficient, almost like the universe has these preferred patterns, these low-energy, high-stability configurations that life can tap into.
And coherence is about alignment with those patterns.
Exactly. Coherence means the system's internal processes align with these universal symmetries, allowing for incredibly efficient energy and information flow. Imagine a quantum-based life form. Coherence might mean that individual quantum states within the system are perfectly synchronized, maybe allowing information transfer or energy channeling with near-zero loss, way beyond what classical physics would predict.
Right.
It's about finding and leveraging those sort of sweet spots in the universe's inherent design, if you will.
And resonance, how does that fit in?
Resonance is how these systems maintain that alignment and maybe even amplify beneficial interactions. It's like a continuous feedback loop where the system's internal dynamics harmonize with that underlying hypersymmetry. This allows it to grow, adapt, and sustain itself with minimal energetic cost.
So for a crystal life form.
For a crystalline life form, maybe it involves specific vibrational frequencies or lattice structures that resonate perfectly with, say, ambient thermal or gravitational fields. This could allow it to incrementally add layers and grow in a highly ordered, energy-efficient way. It implies that the conditions for life aren't just randomly present, but are intrinsically woven together in this elegant, ordered dance. Life essentially tunes in to the universe's fundamental frequencies to emerge and thrive.
So it suggests the universe isn't just passively allowing life, but maybe nudging it, biased towards its emergence in certain elegant ways.
That's certainly one interpretation of this framing. It suggests a deeper, perhaps inherent potential for complexity in the cosmos.
Okay, so this framework lays out 7 essential ingredients for adaptive life, almost like the universal recipe for cosmic existence. Let's start with the first 2, which seem deeply linked. They're about energy and the fundamental fight against universal disorder. Far from equilibrium stability and negentropy, these really sound like the core engine room of any living system, right? No matter what it's made of.
Absolutely. These are the thermodynamic heart of the matter.
Let's dive into far from equilibrium stability, or ALMES. That sounds like a contradiction in terms, doesn't it? How can something be stable yet simultaneously far from equilibrium? It feels almost paradoxical, given, the universe's natural tendency towards everything just balancing out.
It does sound paradoxical, and that's a crucial question about how life operates. It really gets to the heart of thermodynamic biology. Lilien's definition explains that adaptive life, quote, rises in systems that are far from thermodynamic equilibrium, where energy flow allows for the creation of complex structures.
Okay, unpack that.
Think of something simple, like a candle flame. It appears stable, right? It has a defined shape, a consistent output of light and heat. But it's only stable because it's constantly consuming wax and oxygen. It's processing energy. It's far from a chemical equilibrium. If it reached equilibrium, it would just be inert soot and gas.
Ah, I see.
Life is precisely like that. It maintains its incredibly complex and ordered structure by continuously using energy, by being in a constant state of energy throughput, never truly settling into an inert equilibrium state. To stop that flow is, well, basically the definition of death in this context.
So what does it need for this continuous flow? The document mentions specific parameters.
Right, three crucial parameters. First, sufficient and sustained energy gradients. This is the fundamental fuel source. For us here on Earth, it's often the sun's radiation, or maybe chemical energy from deep sea vents.
But for other life forms?
For a hypothetical silicon-based life, maybe it's extreme thermal gradients deep inside a planet, or the chemical potential between different molten salts. For plasma life within a star's magnetosphere, it could be harnessing magnetic field lines or absorbing high-energy particles. The key is it has to be sustained, not just a one-off burst.
Okay, it's synced energy. What else?
Second, continuous exchange of energy and matter. This is what's called thermodynamic flux. Life isn't a closed box. It can't be. It needs to constantly take things in. It could be nutrients, light, charged particles, whatever, and put things out. Waste products, heat, maybe dissipated electromagnetic fields.
The intake and exhaust.
Exactly. This constant inflow and outflow is what keeps the engine running. It allows the system to essentially shed disorder, or entropy, externally, while maintaining its own internal complexity. For, say, crystalline life, this might involve slowly absorbing and releasing specific mineral ions from its surroundings, allowing slow but steady growth and structural renewal.
And the third parameter, something about instability.
Yes, local instability, which refers to fluctuations that drive new forms of organization. Now, this isn't just random chaos. It's more like small, dynamic shifts or disturbances within the system that actually allow new structures, new adaptations, maybe new levels of complexity to emerge, that pushes the system to new, more organized states.
Instability can be constructive.
Potentially, yes. For a crystalline organism, maybe subtle, periodic thermal fluctuations could be these local instabilities, prompting tiny rearrangements of its lattice structure that over time improve its energy absorption or internal processing. For plasma life, maybe shifts in the surrounding electromagnetic fields force a rearrangement of its charged particles, leading to more stable or more efficient configurations of its coherent structure. It's not about seeking absolute rigid stability, but about harnessing a kind of constructive disequilibrium that acts as a continuous catalyst for emergent order and adaptation.
Okay, so the big picture here is that life isn't static. It's not a thing. It's a process.
Exactly. It's about maintaining structure through constant energy expenditure and exchange, not by just being still or inert. It's how complex order emerges from the background tendency towards disorder, but only through this continuous throughput of energy and matter, and even leveraging small instabilities. It's really a testament to the incredible organizational power that can arise from sustained energetic imbalance.
It really does recontextualize our own existence. You know, we think of ourselves as stable beings, but we're actually these incredibly dynamic, energy-hungry systems, constantly orchestrating this localized defiance of the universe's slide into disorder, and even using little instabilities to innovate and adapt. That's quite profound.
It is. We are walking to talking examples of far from equilibrium systems.
And intimately connected to that constant energy flow is the second ingredient, negentropy, or ALANs. This is where life seems to actively defy the universe's tendency towards disorder, the famous second law of thermodynamics. It's like life is constantly pushing back against the universe's desire for everything to just spread out, equalize, decay.
You're touching on an absolutely fundamental point. Negentropy is defined here as the measure of order and information in a system, driving the emergence of complex, organized structures. While the universe as a whole tends towards entropy-increasing disorder, randomness, homogeneity, life manages somehow to create and maintain incredible levels of order and complexity within itself.
It's like a little island of order in a sea of chaos.
A very active island. It's a localized, temporary victory against the entropic tide. It effectively concentrates order, increases information content within its boundaries.
So how does it do this? How does it win this battle, even locally? The document mentions specific mechanisms.
Right, several key parameters. First, and this is crucial, mechanisms for exporting entropy to maintain internal order. This is called entropy flow. Life is inherently messy in a way. It takes in highly ordered energy, sunlight, complex food molecules, uses that energy to build and maintain its own highly organized structures.
Like proteins, cells.
Exactly. And then it releases disordered waste products and heat, which are basically forms of entropy, back into the environment. This externalization of entropy, pushing the disorder outside, is absolutely crucial for maintaining internal organization.
So like you said, taking out the trash.
Precisely. Think about keeping your house tidy. You expend energy putting things away, creating order locally, but you also have to take out the trash and let heat escape export entropy. Without the latter, the former becomes impossible. For, say, a silicon-based organism in a high-temperature environment, maybe it sheds excess thermal energy as structured waste heat, preventing its internal structures from melting or degrading.
Okay, so exporting entropy is key. What else?
Second, information storage and transfer, which is described as essential for adaptation and evolution. This is where the blueprint for that order, that complexity, is encoded, passed on, and refined over time.
Like DNA for us.
Like DNA in carbon-based life, yes. It's an incredibly dense information storage system. But in exotic forms, it could be other kinds of highly organized information, maybe the precise stable patterns within a quantum coherent field, or the stable energy states in a plasma structure, or even the sequential layering pattern of growth in a crystalline entity. The ability to reliably store and transmit this blueprint for order is absolutely paramount.
And the third point, something about modulation.
Yes, entropy modulation. The system's ability to modulate and regulate its own entropy. This isn't just blindly exporting disorder, it's a controlled, sophisticated process. Life actively manages how and when it generates and sheds entropy, optimizing its internal state, maintaining a dynamic balance. It's about internal regulation. For instance, a hypothetical quantum organism would need incredibly precise mechanisms to dissipate excess energy without destroying its delicate quantum coherence, maybe through controlled photon emissions that carry away entropy but don't disrupt its stored information.
So it's not just dumping waste, it's smart waste management.
In a manner of speaking, yes. It highlights the critical roles of continuous energy input and the sophisticated management of both information and order in sustaining life. Life is, in essence, an information processing and storage system that uses energy to constantly fight against the decay of that information, that order. It's an active, ongoing process of maintaining complexity against all odds. Without these mechanisms, any complex structure would just rapidly dissipate into thermodynamic equilibrium.
So the very act of living is this constant active process of local tidying up and, well, cosmic littering. Life persists by maintaining its internal order precisely because it exports its mess, its entropy, into the wider environment. It's a powerful way to think about this fundamental battle. Okay, so we've talked about the internal dynamics, the energy and order, the engine room that keeps life running. But even the most sophisticated engine needs, well, a stable place to operate, a suitable home, and all its internal parts need to work together in perfect sync. That's where Lilien introduces the next two ideas: benign local cosmology and coherence. Essentially, life's cosmic address and its internal symphony.
Exactly. Life doesn't exist in a vacuum, literally or figuratively. It needs the right setting and internal harmony.
Let's start with benign local cosmology, or ALBLC. That sounds like a very elegant, almost understated way of saying a nice, safe neighborhood for life to emerge and thrive.
What are the critical elements of this cosmic nice neighborhood that the document emphasizes are fundamental prerequisites for any kind of adaptive life, no matter how tough it might seem? It is a nice way of putting it, but with incredibly high cosmic stakes. The definition states, the local cosmological environment must be stable enough to support the emergence and sustenance of life. Life needs a stable stage, right? A predictable backdrop on which to perform its complex, very long-running play. Without that foundational stability, even the most robust internal mechanisms for fighting entropy or maintaining energy flow would just be overwhelmed and destroyed.
Makes sense. You can't build a house during a constant earthquake.
Precisely. And Lilien highlights three fundamental aspects of this stability. First, a radiation environment with a balance between protective shielding and energy input.
The Goldilocks zone idea, but broader.
Broader, yes. Too much high-energy radiation, intense cosmic rays, frequent powerful stellar flares, maybe gamma ray bursts from nearby supernovae, can just shred complex molecules, ionize atoms, destroy genetic material, preventing life from ever forming or persisting. But conversely, too little energy input from a star or whatever the local source is means there's no initial spark. There are no sufficient energy gradients to drive those crucial, far from equilibrium systems we just talked about.
So you need energy, but not too much destructive energy.
Exactly. Earth's atmosphere and magnetosphere are a perfect example of this delicate balance. They shield us from the worst of the sun's radiation and cosmic rays, while the sun provides consistent, life-sustaining energy. For life emerging, say, on a planet orbiting a very active red dwarf star, its benign local cosmology might involve having a much denser, perhaps reflective atmosphere, or maybe living deep underground or underwater to mitigate that intense stellar radiation.
Okay, radiation balance. What's next?
Second, gravitational stability, which the document says ensures structural coherence. Life, whatever its form, needs a predictable and relatively gentle gravitational field to build and maintain its complex structures. Imagine trying to form complex structures, whether it's trees like on Earth, or those hypothetical coherent plasma blobs, or even self-replicating crystals under extreme tidal forces, like near a black hole or in a tight binary star system.
Yeah, things would just get ripped apart. Right.
Or imagine regions of highly erratic, unpredictable gravity. Such chaotic conditions would constantly tear apart any organized structures, making it impossible for them to maintain coherence or build complexity over time. Even for something seemingly formless like plasma life, a consistent gravitational field might be crucial for maintaining its internal field structure, or maybe density gradients necessary for its function.
Predictable gravity. Got it. And the third element?
Third is protection from catastrophic events. This refers to safeguards against things like frequent large asteroid or comet impacts, nearby supernova explosions whose radiation could sterilize entire planets, or sudden, dramatic shifts in a star's energy output.
Basically avoiding cosmic extinction-level events too often.
Pretty much. Life, especially complex, evolving life, needs sufficient time, often hundreds of billions or even billions of years, to evolve and develop complexity without being constantly reset or extinguished or forced back to square one by these cosmic calamities. It needs long stretches of relative calm for its adaptive processes to really unfold. A planet forming in, say, a very crowded, chaotic stellar nursery, constantly being gravitationally jostled by passing stars and pelted by debris, simply wouldn't provide this benign environment for the long haul.
So the analysis here is that life isn't just about the local chemistry or physics.
Not at all. It's profoundly intertwined with the vastness and the relative stability of its cosmic surroundings. A truly benign environment allows for the long-term, uninterrupted development and continuity required for any kind of complex adaptive life to take hold and flourish. It really underscores that life is a cosmic phenomenon, shaped as much by galactic dynamics, stellar evolution, and planetary formation processes as it is by local biochemistry.
You know, we often take for granted how unique and maybe even special Earth's position in our solar system is, and all its protections, our atmosphere, our magnetic field, even Jupiter acting like a gravitational vacuum cleaner.
Quite a list.
It is. And this framework highlights that such conditions aren't just a given out there in the universe. They are, in fact, fundamental prerequisites for any kind of adaptive life, no matter how exotic its form might be. It really makes you appreciate our little cosmic address and how many, many boxes had to be checked over billions of years before complex life like us could even begin to exist.
It certainly puts our existence in perspective.
Now let's talk about the fourth ingredient, coherence, or AL.CO. This seems to speak to the unified, integrated operation of a system, how everything works together smoothly. What does that look like across the incredibly diverse forms of life this document imagines? From carbon-based us to plasma, maybe even quantum life. How do these disparate systems maintain their internal symphony to function as a unified whole?
This is where it gets really interesting, I think, because it speaks directly to the interconnectedness at a fundamental level. And it links back beautifully to that initial framing idea of hypersymmetric coherence and resonance. Coherence, as defined here, refers to the resonance and synchrony of processes that allow the system to operate as a unified whole.
So it's not just a bag of parts.
Not at all. Life isn't just a collection of components or processes existing near each other. Those parts have to work together harmoniously in a deeply integrated fashion for the system to be considered alive and adaptive. It's all about collective behavior, synchronized action, not just individual components doing their own thing.
How does the document break that down? Are there different kinds of coherence?
Yes, it highlights very specific elements. First, there's phase synchronization, which is the alignment of oscillatory and wave-like phenomena. Think about how your heart cells beat in a near-perfect synchrony, or the synchronized firing of neurons that creates brainwaves, or even the precise cyclical timing of complex chemical reactions occurring within a single cell. These rhythmic alignments are absolutely critical for organized function.
Okay, like internal clocks working together.
Exactly. For a crystalline life form, this might involve the synchronized vibrations of its entire atomic lattice, ensuring energy and information flow smoothly and efficiently through its structure, almost like a precisely tuned crystal oscillator in electronics.
Fascinating.
Second, and this is really profound, quantum coherence, which the document says enables efficient energy transfer and communication. This is deep stuff, suggesting that life at its core might leverage strange quantum physics for extreme efficiency, moving way beyond classical limits.
Like what? How would that work?
Well, imagine a photosynthetic molecule in a plant. Instead of light energy just randomly bouncing around until it finds the reaction center, quantum coherence might allow it to explore multiple pathways simultaneously via superposition and instantly find the most efficient route, channeling energy with near-perfect, almost zero-loss efficiency.
Yeah.
Or perhaps a form of communication within a complex plasma or even a quantum-based system that utilizes quantum entanglement for ultra-fast, highly specific information transfer across its entire structure, instantly coordinating actions. This implies that life isn't just classical chemistry. It might be tapping into the very fabric of quantum reality for its most fundamental operations, achieving levels of efficiency and coordination we can barely even fathom.
But wouldn't those quantum states be incredibly fragile?
Extremely fragile, yes. Such systems would require exceptionally stable, low-noise environments, linking back to that benign local cosmology to maintain these delicate quantum states.
Okay, so phase sync, quantum coherence. What's the third type?
The third is macro-scale coherence, which ensures stability and functionality across scales. This means a unified, coordinated operation that bridges the gap from the tiniest components in individual molecules, maybe quantum states, all the way up to the entire organism, or potentially even a colony or a larger collective system. All levels must be effectively singing from the same hymn sheet, maintaining their integrated function.
So coherence from the small scale all the way up to the large scale.
Right, for a large, self-organizing plasma entity in a planetary magnetosphere, macroscale coherence would mean that the behavior of individual charged particles, the formation of local electromagnetic eddies, and the overarching field structure that defines the entity all work together seamlessly, maintaining the entity's overall form and its energy-gathering capacity.
So this principle really highlights the essential unity of a living system.
Absolutely. From the microscopic quantum realm, potentially, to the macroscopic observable organism, all components must resonate, align, and synchronize for the system to maintain itself and function effectively. It implies this elegant, integrated dance of processes where timing, connection, and coordination are paramount. It's not just about what parts you have, but how perfectly they interact to create a persistent, self-regulating, unified whole.
It reminds me of an orchestra. You can have all the best musicians, the finest instruments, but if they're all playing at the same time but out of tune or out of rhythm, lacking coherence, it's just noise, right? A terrible cacophony.
Exactly.
But when they're perfectly coherent, when their sounds resonate and synchronize under the conductor's guidance, you get a beautiful symphony. Life, as described by this framework, sounds like that symphony, an incredibly complex and harmonious interplay of forces and processes that, at every single level, works in perfect concert. It's a truly elegant concept.
A very apt analogy.
Okay, so far we've talked about these universal principles: energy flow, order, the right environment, internal unity that could potentially apply to any life anywhere. But where the document really drives home its revolutionary nature, I think, is by tackling the fifth ingredient: viable substrates, or ALVS. This is where it explicitly broadens the definition of life beyond what we assume based on Earth. Here's where we truly start to challenge our assumptions, right? Where we abandon our comfortable baselines. This is where the framework really earns its deep dive title, by making us seriously reevaluate the very building blocks of existence.
You're absolutely right. The section raises a critical question. What if our understanding of life's building blocks has just been far too narrow, too confined by our single example here on Earth? The AL Groupset stresses that a viable substrate supports the biochemical or biophysical processes required for life. These substrates can vary greatly depending on environmental conditions and the form of life that emerges.
So the material basis of life isn't fixed?
Not according to this framework. It's a huge conceptual leap. It opens up a universe of possibilities for what life could actually be made of. It forces us to consider that the very material of life is highly contingent on its specific environment. What works here might be impossible elsewhere, and vice versa.
Let's start with what we know, though. Our comfortable baseline, carbon-based life. This is home turf, right? And it's the only example we have, so it naturally serves as our point of reference.
Indeed. And carbon's versatility is undeniable. It's the foundation of life on Earth, as the document notes. It forms diverse and stable chemical bonds that allow for incredibly complex organic molecules, proteins, nucleic acids like DNA and RNA, carbohydrates, lipids, which are absolutely essential for metabolism, replication, cellular structure as we know it.
And usually needs liquid water.
Typically, yes. Liquid water acts as an excellent solvent, facilitating all these complex reactions. But Lilien uses carbon-based life primarily as a jumping-off point, not the end point. It emphasizes that this is just one possible pathway, albeit a highly successful one here on Earth under our specific conditions. Carbon's ability to form long chains and rings, its tetravalent nature forming 4 bonds, and the specific energy levels involved in its bonds are just perfectly suited for the temperatures, pressures, and solvent availability on our planet.
Okay, but what about silicon? It's often touted in science fiction and even some scientific circles as a potential alternative to carbon. It sits right below carbon in the periodic table, shares some chemical similarities. But beyond just forming multiple bonds like carbon, what are the unique constraints or maybe advantages that silicon-specific chemistry would impose on life? Especially when you consider the sheer diversity of functions we see in Earth's biochemistry. Could silicon really do all that?
That's the million-dollar question. Silicon, like carbon, can form multiple bonds, often 4. But its larger atomic size and different electronegativity lead to vastly different chemical properties. The bonds it forms, especially silicon bonds, are generally weaker than carbon bonds, while silicon-oxygen bonds are extremely strong. Think rocks, quartz.
So different chemistry, different possibilities.
Exactly. Hypothetically, silicon-based life forms could utilize silicon compounds, perhaps silanes, silicon-hydrogen, or silicon-oxygen chains, to build their structures and maybe metabolic pathways. But the key here, as the document suggests, is where such life might thrive, especially in environments with high temperatures or pressure where carbon chemistry might not be stable.
Why there?
Because carbon bonds tend to weaken and break down significantly at very high temperatures, whereas those strong silicon-oxygen bonds, for example, are much more robust. So you might find silicon life where carbon life simply couldn't hold together.
Okay. High temps, high pressure. What else would it need? Different solvents.
Almost certainly. Key considerations for this kind of life include the need for alternative solvents. Water tends to decompose many silicon compounds, particularly silanes. So you might need solvents like liquid methane or ethane like on Saturn's moon Titan, liquid ammonia, maybe even something really exotic like sulfuric acid under specific conditions. And they would operate under very different thermodynamic conditions than us.
So we'd be looking for life on planets that look nothing like Earth.
Probably. We might be looking at super-Earths with deep, high-pressure atmospheres where methane or ammonia exist as liquids, or maybe worlds with intense, ongoing volcanic activity providing thermal gradients and unique chemistries, rather than temperate, watery worlds like ours.
And how might it operate? Slower? Faster?
Potentially much slower metabolism. Silicon reactions tend to be less energetic and proceed more slowly than equivalent carbon reactions, partly due to silicon's larger size and the strength of some of its bonds. This could lead to vastly longer lifespans and perhaps incredibly slow evolutionary timescales compared to Earth life. And the way it would store information, definitely not DNA, maybe in complex repeating polysilicate structures like intricate minerals or perhaps patterns in silicone polymers, it would be fundamentally different biochemistry.
Okay, moving even further out there. Plasma-based life. My mind immediately goes to, like, the surface of the sun, or maybe science fiction energy beings. Can you even begin to paint a picture for us of what life looks like when its very building blocks are superheated, ionized gas? I mean, where chemical bonds as we know them are impossible. What kind of biology emerges from a soup of charged particles? This is truly mind-bending territory.
It absolutely is. This is where our imagination really has to stretch, and the document explicitly challenges us to do exactly that. Lilien suggests these forms could emerge from coherent structures within ionized gases, relying on electromagnetic fields and plasma's dynamic properties to organize and transfer energy.
Coherent structures? Like what?
Think of highly organized, self-sustaining patterns within the plasma.
Right.
Maybe complex, stable magnetic field geometries or dynamic circulating electrical currents that maintain their integrity. Instead of having cells with membranes, they might be self-organizing plasma vortices or intricate filaments that hold themselves together through sophisticated electromagnetic interactions, constantly interacting with the surrounding plasma.
So a structure made of fields and flows, not
Yeah.
molecules.
Precisely. Such life would absolutely require stable electromagnetic fields for coherence to maintain its structure against the inherent chaotic forces within the plasma. Its metabolic processes wouldn't involve chemical reactions, but might involve the manipulation of charged particles, perhaps drawing energy directly from stellar winds or planetary magnetospheres or electric currents within nebulae.
And how would it eat or breathe?
Maybe by channeling plasma flows or using controlled electromagnetic pulses for internal communication, and maybe excreting waste by shedding excess charge or thermal energy in structured ways. Critically, as the document points out, this life could exist in extreme environments, such as stars or magnetospheres of planets.
Wow, so we should be looking inside stars or around gas giants.
Potentially. It completely shifts our search parameters away from temperate rocky planets towards these incredibly fiery energetic regions of the cosmos, or the vast electrically charged envelopes around giant planets like Jupiter.
The implications are staggering. How would replication or evolution even work for beings made of charged particles and electromagnetic fields?
That's the core question, isn't it? They wouldn't have DNA. Information might be encoded in the specific complex patterns of their electromagnetic fields, or perhaps in their plasma density gradients. These patterns could potentially be replicated through resonant field interactions, maybe splitting off a smaller, stable pattern.
Like a magnetic field budding.
Something like that, perhaps.
Yeah.
And evolution would then be a process of these field structures adapting and mutating. Maybe slight changes in the field geometry, proving more stable or better at energy capture, driven by changes in the surrounding plasma environment. This pushes the very boundaries of our understanding of what constitutes a system capable of life. It forces us to consider entirely new paradigms for biological processes, where structure is a dynamic, energetic pattern, not a static material one, and metabolism is about manipulating fields and charges.
And then we have the final category under viable substrates, exotic substrates. This sounds like a catch-all for anything truly wild, the most speculative and challenging concepts that Lilien's framework dares us to consider. What sorts of things are we talking about here? What are the deepest depths of possibility that truly push the limits of our current comprehension?
This is where the framework really demonstrates its universal ambition, challenging conventional thought completely. It explicitly includes life potentially arising from crystalline structures, liquid metals, or quantum-based systems. These aren't just thrown out as random ideas. The document suggests they are viable possibilities under the right, albeit perhaps very rare in specific conditions, provided they meet the other AL criteria.
Life in crystals, or liquid metal, like the T1000. Alas.
Yeah.
Maybe not quite like the T1000. But the idea is that these forms might leverage truly unique physical properties for their organization and function. Properties like superconductivity, superfluidity, or quantum entanglement. Imagine systems that can transfer energy with absolutely zero resistance, or flow without any friction, or maybe even process information across vast distances instantaneously due to quantum connections. This hints at a biology that is far less about chemistry as we know it, and much more about fundamental physics, leveraging the weirdness of the quantum world or the collective behavior of electrons in metals or ordered lattices.
Okay, give us some examples. How might crystalline life work? The document suggests crystalline life might grow and replicate by adding layers to its structure, almost like how mineral crystals grow, but in a controlled, information-driven way. It would likely thrive in environments with low entropy and minimal molecular movement, perhaps deep within a planetary mantle under immense pressure, or in extremely cold, quiet conditions in interstellar space where molecular agitation is minimal. Picture incredibly slow-growing, self-replicating crystals using ambient geochemical energy gradients or faint radiation to incorporate new atoms or molecules into their precise lattice structures.
So their metabolism would be geological.
Essentially, yes.
Yeah.
A very slow geology. And their evolution might involve minute structural defects or variations in the lattice pattern that confer advantages in energy capture or structural stability, which then get propagated as the crystal grows or replicates perhaps by fracturing in a controlled way.
In quantum-based life, that sounds even stranger.
Definitely stranger. This could use quantum coherence for information processing, as we touched on earlier, but would require extremely low temperatures to preserve quantum states. We're talking environments near absolute zero. This opens up possibilities in the absolute coldest reaches of space, perhaps within vast, dark molecular clouds, or maybe even associated with ultra-cold remnants like neutron stars, where the delicate nature of quantum phenomena can be maintained against thermal noise.
How would such an organism even perceive reality or adapt?
That's almost impossible for us to conceive. How would it experience its environment? What does adaptation even mean when your very existence relies on preserving these delicate, easily disrupted quantum states? Its consciousness or interaction with reality might be fundamentally non-local, maybe based on entanglement patterns. Its metabolism might involve manipulating quantum tunneling or zero-point energy. This category truly is a testament to the AL framework's ambition. It dares us to ask if life is an emergent property of any system, crystal, plasma, quantum field, whatever, that can successfully meet these 7 fundamental criteria, regardless of its material composition or the energy scales involved. It forces us to confront the possibility that life might be profoundly weirder than we ever imagined.
Okay, we've discussed the internal engines, energy, and order. We've talked about the external home, the benign cosmology, and we've explored the very fabric life might be made of the viable substrates. Now we turn to the last 2 ingredients, which really capture what makes life adaptive and persistent. It's about its capacity for change, for self-creation, and for just keeping going. These are the dynamic capabilities that allow life to not just exist, but to endure, evolve, and truly thrive in an ever-changing universe. Let's talk about adaptation and evolution and self-organization and autopoiesis.
Right, these final 2 really get to the dynamism and resilience inherent in the concept of adaptive life.
So ingredient number 6, adaptation and evolution, or ALAE. This seems pretty fundamental to our understanding of life, certainly life on Earth. But how does this framework articulate it for these wildly diverse forms we've been discussing? Is it still basically Darwinian natural selection, or something more universal that could apply equally well to crystalline or plasma forms?
It's framed as absolutely essential for long-term survival and any kind of increasing complexity, regardless of the substrate or the environment. The definition is clear and universal. The system must adapt to changes in its environment and evolve over time, leading to increasing complexity. Life isn't static. It can't be if it wants to persist. It's a continuous process of becoming, a relentless journey of responding to challenges and exploring new forms, new possibilities. Without this capacity, life would be incredibly fragile. Any significant environmental shift could mean extinction.
So what are the universal mechanisms for this adaptation? How does it work across the board?
The framework identifies several key parameters that seem universally applicable. First, mutation and variation. There have to be mechanisms for introducing variability. This is the raw material for change, for innovation. For carbon-based life, we know it's largely genetic mutation, recombination, things like that.
But for the others?
For others, it would look different, but the principle is the same. For a crystalline entity, as we speculated, maybe it's the occasional random misplacement of an atom or molecule in its lattice during replication or growth, creating a new structural motif. For plasma life, perhaps fluctuations in ambient magnetic fields or high-energy particle impacts could induce slight, heritable variations in its energetic configurations or field patterns. The key is that this variability must be heritable in some form, passed down to offspring systems, or maintained through growth.
Okay, variation is the input. What drives the selection?
That's the second parameter. Selection pressures. These are the conditions that favor survival and reproduction of certain variations over others. The environment essentially acts as a filter. A crystalline life form with a lattice structure that's slightly more efficient at absorbing scarce minerals in its environment would be favored and would outcompete others. A plasma life form that develops a field configuration better able to shunt harmful radiation or draw energy more effectively from fluctuating background fields would thrive and propagate its structure. This drives the direction of evolution, selecting for fitness in a specific context.
Makes sense. Variation and selection. What else?
Third, feedback mechanisms, described as adaptive feedback loops. Systems need to be able to learn and adjust based on previous outcomes. Successful strategies or structures get reinforced, while unsuccessful ones are discarded or modified. This allows for fine-tuning and more rapid responsive changes rather than just purely random walks. For instance, maybe a quantum-based life form has internal quantum sensors that detect minute environmental shifts. These could trigger rapid probabilistic adjustments to its overall quantum state to optimize its energy absorption, and the successful adjustments get somehow stabilized or reinforced.
Learning from experience, essentially.
In a broad sense, yes. And the fourth parameter is crucial. Open-ended evolution. This is the capacity for indefinite evolution. Life shouldn't just adapt to a fixed state and then stop. It should, at least in principle, always be able to explore new forms, new functions, new ways of interacting with its environment, potentially leading to ever-increasing complexity over vast timescales. This isn't just about surviving the next challenge, it's about the potential for ongoing innovation, diversification, and perhaps even increasing ecological integration, a truly limitless potential for novelty.
So the analysis here is that life is inherently dynamic, capable of continuous innovation.
Exactly. It's not about perfecting a single, static form, but about the ongoing process of responding, changing, and becoming. This constant interplay between variation, selection, feedback, and open-ended potential seems to be a universal principle of persistence, regardless of the chemical or physical basis of life. It's how systems navigate unpredictable environments and become more robust over time, ensuring their long-term survival in a universe that is itself constantly evolving.
We see this constantly on Earth, don't we? From the incredibly rapid evolution of antibiotic resistance in bacteria, which is a stark, ongoing evolutionary battle demonstrating incredible adaptive speed, to the much slower, gradual evolution of complex animals over millions of years. This framework suggests this fundamental principle of dynamic change and adaptation applies universally, allowing even the most unimaginable forms of life to play the long, long game of survival in the cosmos. It's truly a testament to life's persistent, relentless drive. Okay, on to the seventh and final ingredient, which is particularly fascinating: self-organization and autopoiesis, or ALSO. Now, self-organization makes intuitive sense. We see patterns emerging spontaneously from simple rules all the time, like snowflakes forming or sand dunes, or even a hurricane organizing itself out of warm water and air currents. But what does autopoiesis add to that? It sounds much more active, like life is not just creating order, but actively creating itself, defining its own existence from moment to moment.
That's a great way to put it. This concept is indeed foundational to understanding life's active role in its own creation and ongoing maintenance. Self-organization, as you said, is a more general phenomenon. It's the spontaneous emergence of order and structure within a system. It happens in non-living systems, too. But autopoiesis, a term coined by biologists Umberto Maturana and Francisco Varela, is deeper and much more specific to life or lifelike systems. It describes systems that are not only self-organizing, but also self-producing.
Self-producing.
Yes, autopoietic systems continuously regenerate and maintain themselves, producing their own components and actively distinguishing themselves from their environment. It's this ongoing, active process of boundary setting, self-repair, and self-making that defines what it means to be a distinct living entity. It implies a fundamental operational closure and autonomy.
Okay, that sounds crucial. How does Lillien's framework break down autopoiesis? What are the key features?
The document provides 5 very specific parameters here, which are critical for truly understanding this concept in a universal context. First, autocatalytic networks. These are defined as reaction networks that catalyze their own formation and perpetuation, essential for metabolism and growth.
Like a snake eating its own tail, but productively.
Sort of.
Mm-hmm.
Imagine a chemical cycle where each product helps create the next reactant, and eventually the cycle recreates the starting materials and the catalysts themselves. It's a self-sustaining, self-reinforcing loop that builds itself. For plasma life, this might be a dynamic series of electromagnetic interactions that continuously generate the necessary field configurations and charged particle flows needed to sustain its own structure and energy capture.
Okay, self-fueling cycles. What's next?
Second, compartmentalization. This is the ability to form distinct, enclosed regions where life processes can occur, protecting against external perturbations. This is obviously like a cell membrane in biology, creating a defined inside distinct from the outside. This allows the system to maintain specific internal conditions, concentrations of chemicals, energy levels, information states that are conducive to its life processes, buffered from the randomness of the environment.
So internal protected spaces, even for plasma or crystal life.
Potentially, yes. For a crystalline organism, maybe it's the formation of distinct, stable internal pockets or layers within its lattice that facilitate specific controlled reactions or protect sensitive information structures shielded from the bulk environment. For quantum life, this could involve the creation of isolated quantum domains or error-correcting codes that shield delicate quantum states from decoherence.
All right, parameter 3.
Third, closely related, is autopoietic boundaries. This is the system's ability to generate and maintain its own boundaries, actively separating itself from its environment. This isn't just a passive wall like compartmentalization might imply. It's a dynamic, self-generated, and actively self-repairing barrier that defines the self of the system.
So the boundary itself is part of the self-production process.
Exactly. A plasma entity might actively generate and maintain its own containing magnetic fields to define its edge. constantly regenerating them or repairing any breaches caused by external fluctuations. A crystalline life form might actively deposit new layers onto its surface to repair damage or to grow, reinforcing its self-defined perimeter through its own activity.
Okay, boundary maintenance. Number 4.
Fourth is hierarchical organization. This refers to layers of organization, from simple molecules to complex systems, each building on the stability and coherence of the lower levels. Think about life on Earth. From atoms to molecules to complex macromolecules like proteins, to organelles to cells to tissues to organs to a whole organism. Life is built in these nested, stable layers, with complexity emerging at each level. A complex quantum organism might have similar layers of increasing complexity, from individual entangled particles building up to coherent quantum networks, contributing to overall system-wide quantum processes, with each level supporting the integrity and function of the next.
Makes sense. Layers of complexity. And the last one.
Finally, number 5 is autonomy. This is the system's capacity for sustaining its organization and adapting to environmental changes through self-production and self-regulation. This really sums it all up. It's the ultimate self-made system, a dynamic, operationally independent entity that actively governs its own existence, maintains its identity, and regulates its internal state in a changing world. It's the summation of all the other autopoietic parameters, allowing the system to operate as a truly independent agent within its environment.
So the analysis here is that autopoiesis really underlines life's active role in its own existence.
Absolutely. It's not just passively existing or being pushed around by physics and chemistry. It's actively defining itself, producing itself, repairing itself, and rebuilding itself in a continuous loop. It demonstrates a profound independence from its surroundings while, paradoxically, simultaneously interacting with them through metabolism and adaptation. It's this dynamic, ongoing process of self-creation and self-definition that truly sets life apart from merely complex, self-organizing but non-living phenomena like hurricanes or crystals that don't produce their own components or boundaries.
It really makes you think about your own body differently. Constantly replacing cells, circulating blood, regulating temperature, fighting off invaders. Your body is continuously making you. You are this ongoing autopoietic process.
Exactly. You are a continuously self-producing, self-regulating system, actively maintaining your own boundaries and internal milieu. You are profoundly autopoietic.
This concept really brings home how active life is in its own perpetuation. It's not just a collection of parts assembled by chance, but a self-generating, self-sustaining entity that actively builds and maintains itself. It's a powerful idea.
It truly is. It emphasizes the inherent agency and persistence of life.
Okay, so we've taken this rigorous journey, really deconstructing these 7 essential ingredients for adaptive life from Philip Lilien's groundbreaking work. We've got far from equilibrium stability, AO, AFUS, negentropy, ON, benign local cosmology, ALBLC, coherence, ALSECO, viable substrates, adaptation and evolution, ALSECO, and finally self-organization and autopoiesis, ALSO. We've looked at each piece in considerable detail, exploring its meaning and its potential manifestations across even the most unimaginable forms of life. So let's try to put it all back together now. What does this all mean when we see them not as separate items on a checklist, but as a whole, integrated system? How do these intricate components form a holistic, functional picture of adaptive life?
That's the crucial final step, isn't it? Because what's truly fascinating here, and what the framework strongly implies, is that these principles are not isolated. They're not independent variables. They're profoundly interdependent. They form this robust, interconnected web where each condition supports, enables, and influences the others. You can't just pick and choose a few. They all have to be present and interacting in this dynamic synergy for adaptive life, as defined here, to truly emerge and persist.
Like links in a chain, or maybe more like a web?
More like a web, definitely.
Oh.
Because the failure or absence of even one often undermines the entire system, cascading through the others. They mutually reinforce each other.
Can you give us some concrete examples of this interdependence, maybe applying them across different potential substrates?
Sure. Let's take coherence, AL.co, again, that synchronized operation. As we discussed, this principle enables highly efficient energy transfer, which is absolutely crucial for maintaining far from equilibrium stability, ALS. It also facilitates sophisticated information storage and processing, which is central to generating and maintaining negentropy, ALNA, the system's internal order.
Okay, so coherence helps with energy flow and order.
Exactly. Without, say, the precise, perhaps quantum-level coherence in a photosynthetic carbon-based organism, sunlight energy wouldn't be captured efficiently enough. This would weaken its ability to maintain its far from equilibrium state. It couldn't fuel itself properly, and hinder its ability to build complex, ordered molecules. Its negentropy would decrease. For a plasma life form, if its internal electromagnetic fields lack coherence, it would be unable to effectively channel energy from its environment or maintain its structure, quickly losing its far from equilibrium stability and succumbing to entropy, basically dissolving back into chaotic plasma.
So coherence underpins the first two. What about the environment?
Right, let's consider benign local cosmology, AL.BLC, that stable protected cosmic address. Without it, the structural coherence, AL.SAY, of any system simply couldn't be maintained over meaningful timescales. Imagine a delicate crystalline life form that requires extremely low stable temperatures to maintain its precise lattice structure and its slow negentropic processes. If its local cosmology suddenly changed, maybe its star system drifted into a hot nebula, or it got hit by intense radiation, exposing it to erratic thermal energy, its internal coherence would shatter, its far from equilibrium state would collapse as it heated up, and it would cease to exist as an ordered system. The stability provided by its environment is an absolute prerequisite for its internal organization to flourish and persist.
The cradle is essential for the baby to thrive.
A good analogy. And then crucially, there's autopoiesis, ALSO. This seems to act as the overarching principle that ensures the continuous maintenance and integration of all the other conditions. It's the active, self-producing, self-regulating engine that constantly rebuilds and defines the system.
So autopoiesis ties it all together.
In a way, yes. This active self-maintenance keeps the negentropic AL.AIN processes running by continuously producing components and exporting entropy. It sustains coherence, AL.CO, by actively repairing and regenerating internal structures and boundaries. It actively leverages the specific viable substrate, ALVs, it's made of, to maintain its far from equilibrium stability, ALFs, organizing energy, flows through its self-produced structures. It is this continuous, dynamic self-making that binds the entire system together as a unified, persistent entity, and it's what ultimately enables adaptation and evolution, ALAE, to occur over long timescales by ensuring the continuity of the reproducing system.
So if autopoiesis fails,
If an autopoietic system, say, a silicon-based organism in some hypothetical methane ocean, loses its ability to regenerate its compartmentalizing boundaries or its internal catalytic networks, it loses its distinction from the environment. Its internal order dissipates, its energy flows stop being organized, coherence breaks down, and evolution grinds to a halt. One principle really cannot exist in isolation without the others. They form this tightly woven, mutually reinforcing web.
that interdependence really emphasizes that life is fundamentally a dynamic process, doesn't it? Not a static state, not just a collection of properties.
Absolutely. It's all about continuous energy and information flow, constant adaptation, and vigorous self-generation. It's this ongoing negotiation with the environment, a relentless push towards maintaining order and complexity that actively resists the universe's background tendency towards disorder and decay.
And the biggest takeaway from Lilien's work, then, is this truly universal perspective.
I think so. The Foundations for Adaptive Life offers a substrate-independent and potentially truly universal definition. It deliberately moves beyond our Earth-centric biological assumptions. It invites us, maybe even compels us, to look for life in places and in forms we previously dismissed as impossible or just relegated to science fiction. It's a huge shift in how we think about the cosmos and its potential. We move from just looking for Earth 2.0 to considering the vast spectrum of what life could embody across every conceivable physical and energetic landscape. It truly liberates our understanding of biology, encouraging us to look for these universal processes and interdependencies rather than just specific chemical components as the true indicators of life, wherever it might be found. #outro.
Well, we've taken quite a journey today, a really deep dive into Philip Randolph Lilien's Foundations for Adaptive Life. We've explored this truly universal framework for understanding what life truly is, pushing far beyond our familiar carbon and water bias.
We really have. We've gone from the fundamental need for continuous energy flow and the creation of order against chaos
To the critical role of a stable cosmic environment and the breathtaking interconnectedness, the coherence of all living systems.
Then we challenged our wildest assumptions by considering the astounding possibilities of exotic substrates from silicon and plasma all the way to potentially crystalline or even quantum-based life.
And finally, we explored the unstoppable drive of evolution and self-creation, that principle of autopoiesis that allows life not just to exist, but to persist and thrive across the vastness of the cosmos. This deep dive, I think, has shown us that life, as defined by this AL group set, is potentially a cosmic phenomenon of elegant, self-sustaining complexity that could manifest in myriad, truly diverse forms. It challenges us to look beyond our own reflection in the cosmic mirror, to broaden our minds to possibilities that might defy our current imagination.
And to understand that the universe's potential for life might be far grander, far stranger than we've ever dared to admit.
So, as you go about your day, maybe look up at the sky or just ponder the world around you, consider this provocative thought. Lillian's framework presents life as a universal pattern, a set of dynamic principles that transcend specific chemistry or physics. If these 7 interdependent conditions are met, then life, no matter how alien, could potentially emerge. What other unthinkable forms of adaptive life might be out there right now, thriving in conditions we currently consider utterly hostile, just patiently waiting for us to expand our conceptual lens far enough to recognize them?
What further secrets about universal order, about hypersymmetry and resonance, and about life's deepest principles might they hold?
And maybe just as importantly, how does understanding these fundamental substrate-independent ingredients for adaptive life change our perspective on the fragile yet incredibly resilient adaptive life right here on Earth, our own autopoietic, coherent, far from equilibrium selves in all our familiar carbon-based water-soluble glory?
The universe, it seems, is far stranger, far more complex, and potentially far more alive than we've ever truly comprehended.
Definitely something to think about.